shall continue on. Okay, so before the break, we learned confidence intervals for numeric variables, one sample. And then we did hypothesis tests for numeric variable, one sample. Alright, now that it's after the break, we're going to do confidence intervals and hypothesis tests, numeric variables, but now two samples. The concept and the ideas are exactly the same. The only thing that changes is how we calculate the standard error. That formula changes. And then now you have two samples. So you have two x bars, you have two s's, and two n's. Okay? But the concepts are still very, very much the same. And if you remember how to do hypothesis tests for two samples proportions, it's very similar for doing two samples with means or two samples numeric variables. Okay. So we'll start off with the confidence interval first. We are making a confidence interval not for mu, but for the difference between mu1 and mu2. Interval, you got x bar 1, x bar 2. This forms the center of our interval. Okay. So that's the center of the interval, and then we have a plus or minus, and it's always plus or minus the margin of error. Okay? And the margin of error, just like before, is going to be t star times the standard error. So this is our margin of error. Good, okay? T star, we've already talked about how to get t star when we're doing two samples. Do you remember? Yeah, we use n minus 1, and we use whichever is the smaller n. We've got an n1 and an n2, just use the smaller n, right? So for df, use n minus 1 and use the smaller n. Okay. And the standard error, this is the other thing that changes. The standard error is just an ugly formula. Okay, whenever you have two samples, the formulas are ugly. There's not much we can do. S1 squared over N1 plus S2 squared over N2. That's it, yes? Absolutely. For you, no problem. All right. And there we go. And that's it. So it's just a matter of reading the problem, identifying x bar 1, x bar 2, s1, s2, n1, n2, and then plugging them all in. Okay? So read the problem. And then figure out, identify did the honeydew say to the watermelon? I love you, but can't. Alright. Okay. The average weight of the watermelon. 2 L's, 1 L, I don't know. Is 6.4 pounds with a standard deviation of 0.7 pounds. And the average weight of cantaloupe is 3.2 pounds with a standard deviation of 0.5 pounds. I just made these numbers up. So if you come back and tell me the average weight of watermelon is something else, okay, that's fine. Alright, let's make a 95% confidence interval for the difference between mean weights of watermelon and cantaloupe. Alright. Okay, I know some of you guys are still working. Okay, let's go over this. So let's identify the 7 values we need. Alright, x bar 1. Okay, it doesn't matter, you just have to stay consistent. Whether you call watermelon group 1 or cantaloupes group 1. Okay? So just because I wrote the watermelons first, we'll call that group 1. Okay? So x bar 1, what's the mean weight of x bar 1? 6.4. 6.4. S1?
4.71.
0.7. And N1? 12. X bar 2? 3.2. S2? 0.5. N2? 15. Good. Alright. What is the T star we're going to use? Well, how many degrees of freedom do we have? 11 degrees of freedom, right? We do n minus 1,
Yep.
but we use the smaller n. So we do 12 minus 1 is 11. And I want a 95% confidence interval. So with 11 degrees of freedom, my T star is 2.201. Great. Okay, and so now it's just a matter of putting all of these numbers together. So in the center I put 6.4 minus 3.2.
Yep.
Plus or minus T star, which is 2.201, times the square root. S1 squared is 0.7 squared over N1, which is 12, plus S2 squared, which is 0.5 squared over 15. Is that okay? Alright. So 6.4 minus 3.2, that becomes, I got 3.2, plus or minus 2.201 times, and then when I did this, I got, that's where I got 0.2398. Does that sound right? Okay, check your calculators to see if your standard error is 0.2398. Okay, 0.2395? Close enough, okay? So the center is 3.2, my T star is 2.201, and my standard error is 0.2398. Or 0.2395, something in that vicinity. .5278. So I have, this becomes 3.2 plus or minus 0.5278. Is that okay?
Yep.
So now I have, so 3.2 plus that gives me 3.7278 or whatever. 72 something, 73. And then on the other end, I get 2.7, no, 2 point, what is that?
2.6729 if your SC is
Okay,
0.2395.
672122. Good enough.
Yep.
Alright, so my confidence interval. Alright, so this is, I guess this might be the biggest departure, because this feels, I mean, other than plugging in the numbers into a slightly more complicated formula, it doesn't feel too bad, right? The interpretation just changes a little bit. Okay, so let me write the interpretation here. So I would say I am 95% confident I'm 95% confident that, okay, so this represents mu1 minus mu2, okay, right? We're making a confidence interval. This is the confidence interval for mu1 minus mu2. All right, I wrote that somewhere, okay? The confidence for mu1 minus mu2. Mu1 is what? This is the mean weight of watermelon, and this is the mean weight of cantaloupe. So I write, I am 95% confident that the mean weight of watermelon is between I'm just going to round off to 2 decimals, 2.67 to 3.73 pounds heavier than the mean weight of cantaloupe. Okay, so before we would say I'm 95% confident that the mean weight of this is between this and this. Now, because it's a comparison between mu1 and mu2, I'm 95% confident that the mean weight of watermelon is between this and this, more or less than the mean weight of cantaloupe, okay? So, because we got positive numbers here, we'd say heavier or more. If we had gotten negative numbers, then we would have said this and this less.
Would both of them be negative?
Yeah, both, well, it depends on the confidence interval, okay? So what this says is I'm 95% confident that the average watermelon is between 2.67 and 3.73 pounds more than the average cantaloupe. All right? So is that evidence that watermelons are heavier than cantaloupes on average? Yes.
Yes.
Okay? So that's a situation where the average, so what we're looking for actually, to ask, if somebody asks, do we have evidence that the mean weight of watermelon is more than the mean weight of cantaloupe? Well, the answer is yes. And we're looking for 0. Is 0 in the interval? If 0 is not in the interval, you have evidence that there's a difference. If 0 is in the interval, you will not have evidence of a difference. Okay? So 0 is not, now we'll speed this up. 0 is not in the interval. So we do have evidence that there is a difference between mean weights.
didn't initially ask that, but you're just adding that.
Yeah, I'm just adding this, yeah. Alright, is that okay? Yes.
Explain just the last part again.
So based on our interval, which goes from 2.67 to 3.73, we're asking, do we have evidence that we have a difference between the mean weight of watermelon and cantaloupe? And the answer is yes. We have evidence that there's a difference between the mean weights, because 0 is not in the interval. On the other hand, let me just make up a situation. Let's say we took men and women, and we had them take IQ tests. All right. So maybe 10 men took some IQ tests, 10 women took IQ tests. We create a confidence interval for the difference between the mean IQs, the average IQs. So let's say we make a confidence interval for difference between mean IQ of men and women. Okay, and so let's say the average IQ of the men was 102 and the average IQ of the women was 101, and you go plus or minus. For the 10 women that we did t star times the standard error, okay, et cetera, et cetera, et cetera. So let's say we get 1 plus or minus 3.5, okay? I'm just saying we're making up numbers here. And let's just say this is what our confidence interval turned out to be. So on the high end I get 4.5, and on the low end I get negative 2.5 to 4.5. This is my confidence interval. So this is my 95% confidence interval for mu1 minus mu2. Is that okay? Yeah. Here, I'm going to just put it up, and then I'll write on the other board. So I skipped all the math, and I just said this was our resulting confidence. Is that okay?
Sure.
Thank you. So I've got so my confidence interval for mu1 minus mu2 is negative 2.5 to 4.5. So my interpretation would be I am 95% confident that the mean IQ of men is between 2.5 points lower and 4.5 points higher than the mean IQ of women. This is not a very useful statement. All I'm saying is the mean IQ of men is either lower or it's higher than the mean IQ of women. Well, so do we have evidence that the mean IQ is even different? No. Okay? So because here it's very possible that there is no difference between the mean IQ of men and women. Because 0 is a plausible value because it goes between negative 2.5 and positive 4.5. Okay, so 0 is within our interval. Okay, so we do not have evidence that there is a difference between mean IQ and men and women. Not too bad. Okay, so that's confidence intervals for numeric variables or means when you have two samples. Last topic for today. Excuse me. All right. Hypothesis tests for
Two.
two samples, and we're dealing with means, numeric variables. Okay, just stay with me for another 22 minutes. No? It won't be too bad. All right. Null hypothesis, mu1 minus mu2 equals 0. Okay? Or conversely, mu1 equals mu2. Either way is fine. Just like when we did hypothesis tests for P2 samples, it was P1 minus P2 equals 0, or P1 equals P2, right? And then the alternative is going to be mu1 minus mu2 doesn't equal 0, or greater than 0, or less than 0, depending on how the question is written. Parallel mu1 equals doesn't equal mu2, or mu1 is greater than mu2, or mu1 is less than mu2. Those parallel ones exist also. Right. Again, just like before, read the problem and identify x bar 1, x bar 2, s1, s2, n1, n2. When you read the problem, make sure you can properly say this one is x bar, and this one is s1, and this one is n1, or whatever. Do that, you're in good shape. So with that, we figure out our test statistic. our test statistic is going to be x bar 1 minus x bar 2, technically minus 0, but minus 0 does nothing to it, so we can ignore it, divided by the standard error. Standard error is the same thing that we use for a confidence interval. S1 squared over N1 plus S2 squared over N2. Alright, then you look up the test statistic in the t-table. To get your tail area. Okay? So it's just like we've done before, right? Now we use n. Degrees of freedom is n minus 1, where n is the smaller n, just like before. And get your p-value. Get the p-value, which is either the tail if it's one-sided, or the tail area times 2 if it's two-sided. The p-value equals the tail for one-sided. P-value equals 2 times the tail or two-sided. And I guess the last step would be compare p-value to alpha to decide to reject or not reject the null hypothesis. How do we feel about that? It seems pretty straightforward, right? Or at least in my mind it is. I feel like, you know, the first time you see a hypothesis test and confidence intervals, it feels overwhelming. There's a lot of stuff. But once you get that system down, hypothesis test for one sample proportion, hypothesis test for two sample proportion, or one sample mean, or two sample means, it's all the same idea, okay? The only thing that changes is your standard error and maybe the way you write your hypotheses. And the interpretation is always going to feel a little shaky, but even the interpretation, it's the same concept. You've either rejected the null or you haven't rejected the null. You either have evidence to say that the null is wrong, you have evidence to say that the null is wrong, or you don't have evidence to say that the null is wrong. We would never say we have evidence to prove the null is true. That's just not how we set up our problems. Okay, so let's just do one quick example. I'll put it up on the board. I'll do the example, the answer myself, and then I'll let you guys go home. All right, so let's say we took two samples. We randomly selected 14 cats. We randomly selected 14 cats and 12 dogs. 12, let's say, terriers. You have a terrier? A Yorkie or what? Huh?
A rat terrier.
A rat terrier. I'm not sure what a rat terrier looks like.
You know the mask?
Uh-huh.
Yeah, like that, but like not brown and white, but like black and white.
Okay, alright. What the guy's name is Sparky?
I don't know.
Alright. We took 2 samples, we randomly selected 14 cats and 12 terriers, which are a type of dog if you're not sure. These are little dogs. Alright, okay. We'll say the average weight of the cats is 12 pounds and has a standard deviation of 2 pounds. The average weight of the dogs is 13 pounds and has a standard deviation of 2.5 pounds. Alright. Is this evidence that the average weight of terriers is more than the average weight of cats? It's crazy how all the dogs are related and genetically compatible, right? Like, you can take any 2 dogs, male, as long as they're male and female, and get them to mate and make a totally new type of dog, right? What's that? Yeah, well, I mean, all cats kind of look the same, right? But I'm like, you know, you could take a little Chihuahua dog and, you know, logistics are maybe difficult, but you can get them, like, genetically, like, they could mate with a Saint Bernard and produce a dog in between, right? Who knows, right? Alright, so, in this is the null hypothesis always is going to be mu1 minus mu2 equals 0. Alright? Null hypothesis always has an equal sign, and when it's two sample means, it's always going to be mu1 minus mu2 equals 0. This is almost like a no-brainer step as long as you remember this fact. Okay? You don't have to think about that. You just got to know that. Alright, the alternative though is going to be mu1 minus mu2. Let's say mu1 is the, do we want to label the mu1 to be the cats or the dogs?
Cats.
Okay, so cats will be group 1, and dogs will be group 2. Alright, so in this case we're asking, is this evidence that the average weight of terriers or the dogs is more than the average weight of cats? So my alternative, do I want mu1 minus mu2 to be greater than, less than, or not equal 0?
Greater.
Remember, this is the cats minus the dogs. And we're asking, do the dogs weigh more than the cats? So it'd be cats minus the dogs. If the alternative were true, if cats minus the dogs would be less than 0. Okay? So the hard part is is recognizing which direction your alternative should face. Okay? Alright, so let's x bar 1, s1, n1, x bar 2, s2, and n2. Let's go through the problem and pick all of these out. X bar 1 is the mean weight of the cats, 12 pounds. S1 is the standard deviation of the cats, 2 pounds. N1 is how many cats do I have? 14. X bar 2, mean weight of the dogs, or terriers. 13 S2, 2.5, N2, I've got 12 dogs, okay? So my degrees of freedom is going to be 11. Alright, let's figure out our test statistic. Test statistic is going to be x bar 1 minus x bar 2 minus 0 divided by my standard error. So on the top, I've got 12 minus 13 minus 0. I'm just going to leave that off. And the standard error is s1 squared over n1 plus s2 squared over n2. I've got 2 squared over 14 plus 2.5 squared over 12. Alright, so this I need somebody to do this for me. Okay, square root of 0.8065. This turns out to be 0.898. Is that okay? I guess 0.8981 if you want to keep it fourth decimal. So my test statistic is 12 minus 13 negative 1 divided by 0.8981. I get 1.113. I get negative 1.113. Is that okay? Alright, so we go to our t-table and we look up the row 11 degrees of freedom. And I'm looking for the test statistic 1.113. Okay, so I've got 1.363 is the very first number, and then the next number is 1.796. This corresponds to t 0.100, and this is t 0.050. And so 1.113, I'm just ignoring the negative, goes right here. So my tail has how much? It's going to be more than 10%. Okay? I don't know exactly what it is, but my test statistic is closer to 0 than 1.363. So that means whatever my tail is, it's going to be more than 0.100. Do I double that or leave it for my p-value?
Leave it.
Just leave it as is. So my p-value is greater than 10%. Okay, let's assume I use alpha as 5%. So if alpha is 0.05, my p-value is bigger than alpha, right? P-value is greater than alpha, so do we reject or not reject?
Not.
We do not reject the null hypothesis. Now what does that mean? It means, so the answer to this question, is this evidence that the average weight of terriers is more than the average weight of cats?
Yeah.
We don't have.
No, we do not have enough evidence to say that the average weight of terriers is more than the average weight of cats. Right? So even though I found took 12 random dogs and they weighed 13 pounds on average, and I had 14 cats and they weighed 12 pounds on average, that's not enough evidence to say that the dogs on average weigh more than the cats. So we do not reject the null hypothesis. We do not have evidence that the average weight of terriers is more Great. So study these examples that we've done in class. You can start to take a look at the practice final exam. The practice final exam is posted online. You can start to take a look at that. We have a quiz next week, so arrive on time, and see you then.